Q-learning is elegant, but we built it on a lie of convenience. We assumed we could store the Q function, 16 states times 4 actions, 64 numbers. Trivial. Now imagine the state is a camera image from a self-driving car. Width times height times channels times bit depth. More possible states than atoms in the observable universe. No table holds that. The obvious fix is to replace the table with a function approximator, a neural network that takes a state in and returns Q values out. That's deep Q learning, and it famously gave us DeepMind's Atari agents in 2015. But there's a deeper problem lurking. In many of the domains we care about, robot control, language generation, strategic games, what you really want isn't to rank discrete actions by expected value. You want to choose actions directly, possibly from a continuous space, possibly from a distribution. You want a policy. Today, we flip the problem around. Instead of learning values and deriving a policy, we'll learn the policy directly. This is policy gradients, and it's where modern reinforcement learning actually lives. A policy, written pi theta, is a function from states to action distributions. Parameterized by theta, a vector of weights, usually the weights of a neural network. In our grid world, pi theta of state AS returns 4 probabilities, 1 per action, summing to 1. The agent samples an action from this distribution. Compare this to Q learning. Q gave us numbers we had to convert to actions via argmax. A policy gives us actions directly. The stochasticity is built in, which turns out to be both good for exploration and essential for problems where randomness is part of optimal play, like poker. So we have a distribution. How do we improve it? The answer is embarrassingly direct. If an action led to high reward, make that action more likely. If it led to low reward, make it less likely. That's the whole idea. The math that formalizes this is the policy gradient theorem. The gradient of expected return with respect to theta is the expected value of the gradient of the log probability of the chosen action times the return from that trajectory. Don't memorize the formula. Read the structure. Log probability gradient times return. High return scales the gradient up. Low return scales it down. Actions that did well get reinforced. Why the log probability? Because the gradient of log pi is well behaved. It tells us exactly which direction in parameter space makes the chosen action more likely without blowing up when the probability is small. The simplest algorithm built on this idea is called reinforce. Williams, 1992, predates modern deep learning by decades. The loop is, sample a trajectory by following the current policy. Compute the return, the sum of rewards. For every action you took along the way, compute the gradient of its log probability, scale it by the return, and take a gradient step. That's it. 3 lines of pseudocode. And it works, provably, under mild conditions. The catch, it's noisy. The same policy can produce wildly different returns across trajectories. 2 trajectories run from the same policy can give returns of +50 and -20 by sheer luck. Your gradient estimate is whatever happens to fall out of that run, so it's all over the place, even though the policy hasn't changed. That variance shows up as noise in the gradient, which means slow learning. The entire subsequent history of policy gradient methods, actor-critic, TRPO, PPO, is the story of reducing that variance without introducing bias. Let me show you the key idea. Here's the trick. Instead of scaling by the raw return, scale by the advantage. How much better this action did compared to what you'd expect from this state on average. If you're in a state where every action gives return around +10 and you took one that got +11, the advantage is +1. Modest update. But if every action from this state gives 0 and you got +11, the advantage is 11. Huge update. This reframing is mathematically equivalent in expectation. The gradient direction is unchanged, but the variance drops dramatically. We call the expected return from this state the value function v of s, and in practice we learn it with a second neural network called the critic. The policy network is the actor. The value network is the critic. Actor-critic methods use both. This is the architecture under the hood of most modern RL, from OpenAI's robotics to DeepMind's AlphaStar. One more problem. Vanilla policy gradients are fragile. Take too big a step, and your policy can collapse into something that never recovers. Picture the training log. After one oversized update, the network starts sampling the same action every time, sees no variety, learns nothing, and reward crashes to the floor. Once the policy is stuck, gradient steps can't pull it back. This isn't theoretical, it's a routine failure mode. Performance crashes, and the whole learning process fails. The fix, introduced by OpenAI in 2017, is called Proximal Policy Optimization, PPO, and it's as close as RL has to a default choice today. The idea is a trust region. At each update, PPO measures the ratio between the new policy's probability of each action and the old policy's probability. If the ratio gets too large, meaning you'd be changing the policy too aggressively, PPO clips the objective. Geometrically, it means the optimizer is barred from taking steps that move the policy too far in probability space from where it started. You get aggressive learning inside the trust region and safe behavior at the edges. PPO is what OpenAI used to train the robot hand to solve a Rubik's Cube. It's a key ingredient in the RLHF pipelines that produce modern language models, ChatGPT, Claude, Gemini. When you read, "We fine-tuned with reinforcement learning from human feedback," PPO is usually doing the lifting. Let me pull back and close the arc. We started 3 lectures ago with a simple loop: agent, environment, action, state, reward. We filled it in with Q learning, a table you could hold in your head. Then we replaced the table with a function approximator and saw it break in interesting ways. Then we replaced the function being approximated entirely, values out, policies in. That took us through reinforce, actor critic, and PPO. The frontier right now is racing in 2 directions. One is offline RL, learning entirely from fixed datasets without interacting with an environment at all. The other is using RL to align models trained on massive unsupervised objectives. 3 variants are worth naming. RLHF, reinforcement learning from human feedback, trains a reward model on human rankings of outputs, then fine-tunes against that reward. RLHF, the same idea with AI feedback, replaces human raters with a learned judge. DPO, direct preference optimization, skips the reinforcement learning loop entirely and reformulates alignment as a supervised loss over preference pairs. All 3 are how modern foundation models get shaped into useful assistants. Everything you've seen in these 3 lectures is a prerequisite for reading the current literature. You now have the vocabulary to open a paper from DeepMind or Anthropic or OpenAI and follow the argument. The loop we started with is still there. It's just that now the agent might be a 10 billion parameter neural network. The environment might be a human conversation, and the reward might come from a learned preference model. The loop doesn't care. Thank you for watching. Keep exploring.